have these buttons?
If I click the person, then I get a button. Hello, Martin.
Okay, hello.
Hello.
Okay.
That's great. I assume you want to share your screen for your presentation. Is that correct?
Okay. Yeah. Let me try that. Let's see, where is the share screen thing?
It's at the bottom.
Let's actually try to, if everyone actually hears us.
Share screen.
Yeah, just Martin, were you able to hear us when we were talking on the stage before you joined on the stage? Was that okay?
Yeah. I'm just trying to share my screen.
Okay. So people in out there can hear us, right? So good.
Okay. Yep. Okay, so that seems good.
Okay. Good.
Can I annotate this somehow? Are there ways to highlight parts of the slides in this platform? Do you know?
No, I think it's just going forward and backwards. So if you really want to use a cursor, then you're gonna have to share your screen.
I think we're all new here.
Yeah.
Okay.
I did play around with it when I was in one of the demo sessions, but you can't. There's no pointer or anything like that.
Let me share the screen. It's fine. Let me try. We still have some.
Yeah. It's all on track.
Okay. No, wait. No, I can't do it.
Is it?
Okay.
Thanks, Tati.
No, okay. Let me fall back to the
slides.
Okay, let's go the show way.
Okay. So, are you ready? Will you be okay?
Yeah. Let me just make this one. Somehow I am on the wrong screen here.
Okay, I'll start with some logistics. Okay, Martin?
Okay.
Okay. So, hello everyone. Welcome to this year's Hope. Second year when we are dealing with this new setup for our conferences and workshops. And thank you for coming. Yes, there is still hope. So our first speaker is going to be Martin Odersky, but first a few logistics. This stream is streamed to YouTube as well and recorded. So if you don't want to be recorded, then just stick to the chat and the Q&A, and the session chair will read your question anonymously. Between the sessions, nothing is recorded and streamed, so I'm told. So if you're being shy, you can wait until between the sessions to speak to the speakers. As you can see hopefully as you can see on the conversation tab on the right, you can ask a question in the Q&A, raise your hand. And if you raise your hand, I will invite you to the stage, and then you'll be able to share your audio and video and people can see you. And so we'll see how that goes. And without further ado, let's start our first session. Okay, so Martin, it's with great pleasure to introduce you as our first speaker. Tell us about Monads with capabilities, please.
Okay, welcome everyone. Good morning. For those of you who were this morning, like for me, I'm going to talk about some recent work we did on using a really old result by Filinsky from 1994 to represent monads with capabilities, and this has essentially very important implications for industrial applications today. So let me go into that. Let's see if we can go forward. Yeah. You probably recognize the paper on the left, The Marriage and Effect of Effects in Monads by Philip Wadler and Peter Thiemann. It's probably been one of the most impactful papers over the last 20 years. So much so that now, when many people, when they say effect, they mean monad. Maybe not in this workshop. We are more essentially further away. Yeah, we are more. We know better in many cases, but in the industry at large, that's often what it means. There are many use cases of monadic programs, most of them actually in the domain of reactive and asynchronous programs. So when you have some service somewhere, web service, cloud thing, whatever, it has to process events. And often, if you have people who sort of come from a functional mindset, you use a monad for that, a monad for futures or for tasks, or some super monad that has essentially reader and control and task and error, something like Zio, or I'm sure Haskell has similar monads that do all that. So it goes so far that today often functional programming is perceived as programming in monads in these parts of the industry, which of course is wrong, it's way too narrow, but essentially that's the general impression. So in fact, monadic must have good things going for them, otherwise it wouldn't be so successful. And here are three that we can identify. I believe the first is that, well, monadic values are values, and values are good, right? So because once you have values, you can add a rich interface to those values. And in these cases, reactive asynchronous programming, you have lots of operations that need to be supported and that essentially would add to flexibility if you can support them in a pluggable way. So for instance, scheduling tasks, canceling tasks, tracing tasks, that's all quite difficult and complicated, and these modern monadic frameworks, they provide all that. So that's good. Now, when you have such values, then of course you need to compose them, and there really monads shine, because at the bottom of it, the fundamental operation is sequencing of these things. I mean, you also have parallelism, but that's much coarser. So the fine-grained composition is sequencing, and of course, monads are the right way to express sequencing. But the monadic approach also has problems, and I believe the first quite obvious problem is that monadic code does look like nothing like direct style code. So it's essentially a bunch of binds of flat maps, and there can be syntactic sugar like do notation in Haskell or for expressions in Scala, but it doesn't look anything like direct style. Direct style is much more flexible. You can essentially intersperse println where you want. You can use recursion unrestrictedly, and so on. And furthermore, if you want to switch from one to the other, it becomes very awkward. So let's say you have a nice monadic program, you wrote all your for expressions and so on, and then you want to put a println somewhere in the middle of a function, then that wouldn't work, because the println essentially, no, sorry, it should be the other way around. You have a nice direct style program, everything is pure, everything is functional, is referentially transparent. And now you want to introduce an effect like a println. Well, you have to switch to monadic code. If monads is what you have to express effects, so you have to rewrite your whole program into do expressions or for expressions and so on. The other big problem with monads is something that I believe Oleg was one of the first to notice, that that's that composing several monads is also very awkward. Monads don't really compose very well, and what people usually did was use monad transformers, and that's something that can be quite cumbersome as it scales. So that's why people have looked recently for essentially different ways to do things. There was a year in the Scala community of free monads, and then there was a year of finally tagless. But all these things are a bit heavyweight and difficult to onboard new people, clunky, you could say. So what happens now is that real systems often actually revert to saying, well, let's not compose monads at all. Let's invent a super monad that has everything that we can conceive in it. So it has some environment component, some error component, some result component, and let's just work with that, because it's so much simpler to work in a single monad than with several of them. But of course, that sort of this one-size-fits-all approach is not good for everyone, and definitely lacks modularity. You can't pick and choose your effects anymore. So another new thing that, well, not so new, but a thing that recently gained a lot in popularity was to hide the difficult monadic code with async, something like async. So here you see an example. So we have an async block, and async blocks gives you a future, so something that happens in the future. And inside the async block, you can have other async blocks, and you also can have awaits, and essentially an await waits for a future, and then continues with essentially the future result. So inside an async, you use direct style for everything, but outside, essentially, you get the future. So that avoids you writing all these monadic compositions. That was available, I believe, first in C#. It was itself influenced by workflow expressions of F#. It's also available in Scala 2, in TypeScript, Python, Rust, and many, many other languages. In Scala 2.13, so that's the last version of the Scala 2 branch, we're now in the Scala 3 branch, that allowed async to be compiled, also to be coupled with user-defined monads. So it wasn't just tied to a single thing like a future or a task, but you could essentially determine what it was defined with. So that's actually nice progress, but it will turn out we can do much better than that. So what async essentially does is a syntactic sugar on top of monadic code. That's not always what it is implemented like. So it's often implemented with a state machine or something like that. But at the outside of async blocks, you have a monadic interface, a future or a task or something like that. So you could see these state machine implementations as essentially just a local optimization for a bunch of flat maps. So async is nice because you can use direct style, like I said. So at the top of the slide, you see a typical usage. You have async, and then you have two awaits, x and y, which, let's say, they both give you an int, and you sum them up. But it doesn't really get to more interesting use cases. So the next thing already doesn't work. So let's say, well, let's not just sum two numbers. Let's sum all the numbers in a list, and each number in a list is a future, so we have to wait for it. But unfortunately, we can't write xs.map_await.sum. The problem is that async is a syntactic transformation. So basically, everything that it touches, the compiler has to see. And map is a function, a higher-order function that comes from the standard library, so the compiler can't touch it, and therefore, essentially, the connection breaks. You can't thread async code through code that isn't prepared for it. And that leads to essentially a split in the ecosystem, that you have essentially code that is async and code that is direct. And you have to pick which is which, and they can't essentially take on any other role. So there's a famous essay by Bob Nystrom titled "What Color Is Your Function?" that essentially treats that in a humorous way. It's a very nice essay to read, but it shows a real problem that essentially async invariably leads to this ecosystem split. So if we change the setting a bit and say, well, what these things all did was basically map things back into monads. So, but let's say, well, monads basically pretend that you run on lambda calculus, you run on a purely functional thing, and monads add selectively new functionality, both in the types and in the operational runtime. But computers are not like that. Computers have much richer runtimes. So they have exceptions, they have side effects, and more they also have continuations or coroutines or something like that. I mean, computers can, of course, do all that, they're Turing machines, but I mean actual runtimes on which we're interested to execute our programs. So these things can replace monads if we choose so. We could use exceptions instead of a monad like try. We could use native side effects instead of monads like st for local effects or io for global effects. And we could use continuations or coroutines instead of all these reactive abstractions like future, task, or control. Then we could, in that case, we could avoid monads. But we haven't really gained that much because essentially we lost typing. We lost the typing aspects. We can use all these things in an untyped language or in a typed language that just gives us access to these things, but they don't show up in the types. And that's a problem because we typically want to know about these things. You want to know what exceptions your program throws, because that should be part of the contract. You want to know whether your function is pure, referentially transparent or not. And you also, in particular, you want to know whether something can block or not, or might wait indefinitely or things like that. So all these things are important things to reflect in the type system. But on the other hand, once we decouple the operational semantics from monads, we can also investigate other ways to express the typing. And there are several interesting ones. And one particular interesting way to do the typing of these things is via capabilities, to use capabilities for tracking effects. So instead of saying, I have an effect like an exception, I can throw an exception, I say, well, this code needs a capability to throw an exception. It comes down more or less to the same thing, but capabilities have several aspects that make them quite interesting here. So what about monads then? In the end, we want something like async await, so that can couple with monads, that can glue monads together, but without the restriction. So we want to write it and thread it through map and things like that, and not tied to a specific monad. So we want direct style to interrupt with different monads at the same time. And in fact, that has been done in the semantics a long time ago by Filinski in his paper Representing Monads, 1994. So he showed that we can implement arbitrary control effects in the underlying language if the underlying language has support for composable continuations. The implementation is done with two primitives, reflect and reify. So reflect takes a monadic abstraction, that's the T of A and the type rule, and essentially gets you out of the monad, which is something monads don't provide natively. So it lets you map a M of A or T of A to an A. And reify goes the other way. So it takes a simple computation of type A and turns it into a monadic computation of type T and A. If we go back to the await async framework, then reify is async, so it's on the outside, and asynchronous computation and reflect is on the inside. It's the awaits. So that also means that for safety, we need to ensure that every await or reflect is inside an async reify. We can't have a reflect that's not encapsulated by a reify dynamically. And to ensure that, we can use a capability. So the capability would be provided by the reify, so it would be created by the reify or async on the outside, and it would be passed down to all the locations where we want to await or reflect. And it would also essentially provide the means for essentially then do the control operation that does the await or the reflect. Okay, so that's the principle. How do we represent that in Scala? So we have developed a little library to implement Filinski's ideas and to connect with existing monad stacks of existing libraries in Scala. It's all centered around a trait that represents monads called monadic. So monadic takes a type constructor, that's the M here, and it has the two obvious operations, pure and bind, with the obvious signatures that you know. That's actually the sort of the pure view. In practice, what we used was something slightly different. Instead of bind, we used an operation called sequence, which essentially has trampolining built in. That's because Scala runs on the JVM, which doesn't have tail call elimination. So we have to be careful that we don't overflow the stack, and sequence does that. Sequence is like bind, but the function, it doesn't just return a monadic result with the new result type R, but it can also opt to give you back essentially a signal that it wants to be called again after the stack is unwound. So that's the trampoline functionality. But it's essentially all encapsulated in this framework, so it's not really, user code doesn't really have to deal with it. Okay, so once we have that, we can now define reify and reflect. So reify takes an operation, that's this prog here thing, and runs that. That operation is a direct style operation, and it runs that. And of course, the operation needs to have access to a reflect operation. That's the trait that you see at the top here. So reflect says reflecting on a monad means that I can get out of the monad. I essentially put in a monad value, like a future, and I get back the value of the future without, of course, without blocking. That's because we run in an async context, so everything is essentially on demand asynchronous. So just for those of you who don't know Scala well, this colon monadic here, that's basically a type class. So it plays the same role. It says the type constructor M must have the monadic type class. We call it a context bound, and it's a short form to express an implicit parameter. So we don't have native type classes. We have these implicit parameters that get passed with these using clauses. So what this says is we have reify. It takes a constructor M, and there must be a monadic instance for M that's essentially the compiler can synthesize for us. So that's the using clause. The other piece of syntax here is this question mark arrow thing. That denotes a context function. So we have established that essentially the code inside a reify must somehow know how it can reflect. So that gets passed in as a parameter. But for convenience, we don't want to thread that everywhere through the code. That would be way too burdensome. So we use an implicit parameter instead. And so what this question mark arrow says, it's a function. So it's a function from reflect to A, but it's a function that gets applied implicitly. So it's a function with an implicit parameter, and the parameter gets resolved automatically every time the function is referenced. So that way we avoid the burdensome threading of things through the direct style code. If you want to find out more about that, so there's a paper in Popper 2018 that essentially develops a theory and use cases for these sort of abstractions. So here's a simple use case for our reflection. We have an abort method that essentially takes a reflect of option. So what we want to do is we want to essentially reflect on the option monad, and if you do that direct style, you get essentially something that of computations that can abort. So here's the abort operation. It takes a reflect of option, and it just essentially finishes the computation with none as the value. And then we have a save diff operation. So save diff says if the divisor is 0, then we abort, and otherwise we provide the division. And then we put the whole thing in a reify that says, well, our monad is option, our final result is int, and let's do 2 safe divisions with 4/0 and 5/0. So what this would do is the first time it would hit a safe diff, it would return none. And if the divisor wouldn't be 0 but something else, then it would give you back an optional value, a sum with the actual result. We can also abstract this out a bit. So reflect and reify always makes my head spin a little bit. So we can put that under nice abstraction. So we can define the type optionally A, which is essentially the result A as a result of the implicit function that takes a reflect of option. So we take a reflect of option implicitly and return an A. And then we have a constructor for that, also written optionally lowercase, that says, well, we have an optionally computation and we turn it into an option of A. And that's just a reify. Once we have that, we can write the example nicer. We can write save diff. We can say that's optionally int. And then we run the whole thing in an optionally context. You could say, well, how is that different from option? How's optionally different from option? Well, it's different because what you see here, it's direct style. So we just essentially can have the addition of two safe diffs. We use it directly. We don't try to pull out things from an option with a pattern match or a get or whatnot. So it's direct style. You just write things as on the happy path. That means you get a result, and if something goes wrong, then you essentially abort through a control operation. So that you could have expressed with async, or an option-like version of async, of course. But here's a more interesting use case. You can also say optionally list of 210 map safe diff of 22 with essentially the values in the list. So you go through the list, and each list value becomes a divisor of 22, and then that's the list that you return. And that, as you've seen, you couldn't do with essentially a purely syntactic construction like async, because it doesn't take, essentially map wouldn't know about it. But if you have underlying control that is universal, then of course you can. Okay, so what we can also do is we can combine effects, and that's where it gets even more interesting. So we can say, okay, now that we have optionally can verify an option, we can also reflect on futures. Reflecting on futures is essentially just direct style asynchronous programming. So here you see at the bottom, you see a combination of the two. The inner code says, well, we verify in future. That means that lets us read a text file, and reading in this framework is a future. So at some point in the future, we get the file back. Then direct style, we take its size, and also direct style, we add safe diff 50 to it. So that's now two monads that we have composed. And if the future comes back, we get its size, and we do safe diff 50, then we will exit directly out of the option verify and essentially skip the future verify. So that shows that we can essentially have these layered monads in this style, which if you use something like monad transformer are a big headache, because that means that it's much harder to compose than in this way. So the implementation we have is in Scala on top of Loom. Loom is a native coroutine implementation, currently in an early access JDK. It's hopefully scheduled in some future version of Java Virtual Machine. We don't know yet which one exactly, but it will hopefully be not too long. It's available from the GitHub address that you see here. It showcases integration with several popular monad and async frameworks, including Cat's Effect, Scala Z, Zario, and Scala Concurrent Future. So you see that there are quite a lot of them out there, but the nice part of the generality of monadic reflection is that it works in all of them. Essentially, the only thing an implementation has to do is implement the monadic interface. So in summary, I think the take back is once we have a runtime that supports coroutines or continuations, we can mix monadic and direct style computations with reflect and verify. And that, in a sense, gives us the best of both worlds. It gives us the composability of first-class monadic values, the good parts of monads, but also the composability of different effects. That's where monads had problems. And what's more is we can integrate nicely existing, widely used monadic libraries, and thereby provide a smooth migration path forward, which is interesting, important, because I mean, people have invested a lot in these monadic libraries, and there are many millions of lines of codes written in them. So to put a perspective on that, quite recently Brian Gutz gave an interview. Brian Gutz is the Java lead at Oracle. He said, I think Project Loom is going to kill reactive programming. I believe it's reactive programming. He means these ways to represent things with monads. He has a point in that he says, well, previously, without coroutines and continuations, the only way to get reasonable reactivity, that means essentially that we can have many concurrent operations, most of them are waiting for some events, was with these monadic frameworks. And now with Loom, with native coroutines or fibers, that's no longer necessary. So will it kill reactive programming? I don't know. I think probably Not immediately, certainly, because what is proposed by Loom and Fibers is, of course, a very imperative coroutine implementation, so that solves none of the problems of composability and so on. But in any case, whatever happens, monadic reflection is a good lifeboat for the monad things, because, as we have shown, they let you use the monadic code inside a direct style framework, and it maps to Loom and coroutines. I should say there's one caveat that I have glossed over. Well, there are two. One is Loom only implements specific one-shot coroutines currently, so that means they only work for monads that work with those sort of control operations. So it doesn't work for any monad, but it works for enough monads that I believe are currently of big interest. The other caveat is that once you work with capabilities, you have the problem that like any values, capabilities can be captured in closures. And that can lead to problems if capabilities have limited lifetime, because you want to have a limited lifetime of a capability, then you pass it in the closure, and the closure might survive the lifetime of the capability. So an example is here that you see here. We have a reify option int, and instead of doing two safe diffs additions, we put them under a lambda. And now if you want to try to use that like this, that we say, okay, give me back what you just verified, that will be sum of some operation, a function, let's apply the function, and if not, let's return 0. Then the fiber handling the reify will probably have terminated before the safe diff call aborts, and that would be a runtime error. So that's essentially an inherent problem with current capabilities. And what we're doing also is we're working on type systems that can track ephemeral capabilities. So those are capabilities that have bounded lifetimes. And such a type system could ensure the safety of monadic reflection by preventing that the reflect capability can escape from the scope of a reify. So you see here at the bottom of the slide a link to a paper that we have on arXiv on that. That's it for the talk. Thanks for listening so far, and happy to take questions.
That's great, thanks. So we have a question on the Q&A. Is the layering order of the effects baked into the type of the computation? In the example, the type of the term read file size plus safe div 50 has to match the order that option and future are peeled off.
No, in fact, the option. Yeah, so, well, sure, the layering order is baked into the type of the computation. Yes, absolutely. So the type as seen from the outside is exactly that. But of course, you can simply swap the two things, and if you adjust the types, so you can do it either way. No, wait, sorry. No, the type of the term read file size and plus safety 50 is just int. There's no monad in that type. The type, essentially, the monadic types come when you look at the whole computation from the outside. And in this case, because the outside reflect was on an option and the inside reflect was on a future, you will get an option of futures. If you swap them, you would get a future of options. So the outside, the layers of the reflect determine the type as seen by the outside, but not the inside. In the inside, everything is direct style, so it has the simple types.
So I actually have a follow-up for that. So one issue with monads, as you said, is the modularity, because the type really bakes into the type everything that has to be combined. And one way people get around this by saying language like Haskell is you quantify over all possible monads. You can always say, if you give me a monad and that monad has something, then I can do this. And here you're proposing futures as a little bit of an alternative, but it doesn't seem very flexible, or rather it's ultimately flexible, right? You kind of throw in the whole future in, and that's it. You don't have any tighter control over what can go in the environment and what can. Do you find that's a problem in practice, or how does that pan out in practice from your experience? Would you prefer tighter control?
Yeah. Well, the one system that quantifies all possible monads that I know best is finary tagless. So finary tagless can do that, but it's still it's essentially, I see it as a DSL that's very stylized, very general, but it sort of also requires global buy-in. So everybody has to keep to the same style. And in practice, that's hard to achieve. You have a lot of heterogeneous systems. You can sometimes do it, but so there's currently a big debate ranging over finally tagless versus a single supermonad, and it seems the supermonad people have essentially very strong arguments why this monad parameterization approach is just too complicated. Since I don't write a lot of this reactive code myself, I'm a sort of an interested bystander, so I can't really be the arbiter which one is better. But it seems that it's not a done deal.
Just to add one thing. So if you have code that doesn't use one particular monad in this monadic reflection setup, you don't need to do anything. You can just write your direct style code. So you don't need to quantify over all possible monads. It just works. You just write your direct style code without mentioning any monad, right?
When you're mentioning the future. Oh, okay.
Yes.
I mean, I'm staying away time from your talk. So
no, it's fine. My talk is shorter.
Okay. Do you want to go with the video, by the way?
Oh yeah, if that works.
That should work. Okay. So Martin, thank you very much. There's going to be ample social time to follow up on this.
I'm sharing my screen.
So let's thank Martin again, and let's see if this works. Now I need to find Jonathan's video. Sorry, this is the first time. There you go. Play on stage.